Leave an ordinary steel tool outside for a single winter, and it will come back covered in rust. Leave it buried in damp soil for a decade, and there may not be much left worth recovering at all. Metal corrodes. That is simply what metal does, given enough time and moisture. Now picture pulling a bronze sword out of the ground after 2,200 years and finding the edge still sharp, the surface still clean, and the blade still functional enough that a modern archaeologist could cut with it. That is not a dramatization. It is roughly what happened when excavators reached the weapon deposits buried alongside China's Terracotta Army, and for decades afterward, the most popular explanation for it turned out to be, according to the most rigorous study yet conducted, almost certainly wrong, which somehow makes the real answer more interesting rather than less. The discovery itself was an accident. In March of 1974, a group of farmers near the city of Xi'an in Shanxi province were digging a well during a drought when they struck fragments of fired clay and bronze arrowheads. What they had actually hit was the outer edge of the burial complex of Qin Shi Huang, the first emperor to unify China. And what excavation eventually revealed across 3 enormous underground pits was an army of thousands of life-size ceramic soldiers arranged in formation, each one individually detailed and equipped critically with real functioning weapons rather than ceramic imitations. Those weapons are the part of the story that tends to get overshadowed by the statues. Alongside the figures, archaeologists recovered tens of thousands of bronze objects, arrowheads in the hundreds of thousands, along with swords, spears, lances, halberds, and crossbow triggers. These were not decorative props, they were functional military hardware cast from a copper and tin alloy, with the composition varying deliberately depending on what each weapon needed to do. The swords in particular were made with an unusually high tin content in the range of 21%, which produces a harder, sharper edge than the softer bronze used for components that needed to absorb impact without shattering. When those weapons started coming out of the ground in remarkably good condition, researchers noticed something on their surfaces: traces of chromium. Chromium is the element behind modern chromate conversion coatings, an industrial anti-corrosion treatment developed in the 20th century, and the conclusion that followed was immediate and widely repeated. Qin dynasty metallurgists, the story went, had discovered an anti-rust chromium treatment roughly 2,000 years before it was reinvented in the modern era, and that was why the weapons had survived. It appeared in documentaries, museum panels, and popular articles for decades, and it is still repeated in plenty of places today. In 2019, a research team led by Marcos Martinon Torres, an archaeological scientist then at University College London, working alongside colleagues from the Emperor Qin Shi Huang's Mausoleum Site Museum, published a study in the journal Scientific Reports that tested that assumption directly, and the results dismantled it. The team examined the distribution of chromium across a large sample of artifacts and found that the chromium presence correlated with something nobody had properly accounted for: the lacquer. Many of the weapons had components made from wood or bamboo, shafts, handles, grips, and those organic parts were coated in a lacquer that turned out to be rich in chromium. Over 2 millennia of burial, as the organic material decayed, the chromium from that lacquer migrated onto the adjacent bronze surfaces. Crucially, the researchers found that surface chromium correlated with which type of object it was, meaning whether it had lacquered parts nearby, and did not correlate at all with how well the bronze had actually been preserved. Weapons with chromium on them were not measurably better preserved than weapons without it. The chromium was contamination, not treatment. So if not chromium, what actually kept the weapons intact? The study pointed to a combination of far less glamorous factors, chiefly the soil. The burial environment at the site is moderately alkaline, with a relatively high pH, very fine particle size, low aeration, and low organic content, and every one of those properties independently works against corrosion. Fine, densely packed soil limits how much oxygen and water can circulate around a buried object. Low organic content limits the microbial activity that accelerates metal decay. A moderately high pH keeps the chemistry unfavorable for the reactions that eat bronze. The team also noted that the metallurgy itself contributed, since the high tin content of the bronze, and in some cases trace arsenic in the alloy, both improve corrosion resistance on their own. There is something almost deflating about that explanation on first hearing, until you sit with what it actually implies. The weapons did not survive because of a lost secret technology. They survived because of good alloy design and because of where they happened to be buried. And that reframing points attention at the part of the Terracotta Army arsenal that genuinely is remarkable and that does not require any mystery to be impressive. That part is the manufacturing. In 2014, a team including Xu Li and Martinon Torres published research in the journal Antiquity examining the bronze crossbow triggers recovered from the site. A crossbow trigger is a small multi-part mechanism, and it only works if the individual components fit together precisely. The team analysed 216 triggers recovered from Pit 1, measuring them and grouping them typologically, and found that they clustered into tight subgroups with remarkably little variation between individual pieces, the signature of genuine standardization rather than individual handcrafting. Using portable X-ray fluorescence to identify the chemical signatures of distinct metal batches and combining that with where each object was found in the pit, the researchers reconstructed how the production was actually organized. The picture that emerged was not a single centralized assembly line. It was what they described as a cellular production model, multiple small, multi-skilled workshop units, each producing complete batches of components which were then stored and eventually distributed to equip specific sectors of the buried army. Triggers were cast in molds, filed to precision by hand, and assembled in controlled batches. That distinction matters more than it might sound. A single production line is efficient but fragile, since a bottleneck anywhere stops everything. Distributed cellular units producing standardized, interchangeable output are more resilient and more scalable, and it is a model modern manufacturing rediscovered and formalized in the 20th century. The Qin were running it at scale for a project that historical accounts suggest occupied hundreds of thousands of laborers over roughly 4 decades, coordinating output precise enough that components from separate workshops still met a common specification. So the honest version of the story inverts the popular one entirely. The chromium anti-rust technology, the thing that made headlines for decades, was never real. The weapons survived largely because of alloy composition and burial conditions. But underneath that discarded myth sits something arguably more impressive and considerably better documented: an imperial manufacturing system capable of producing hundreds of thousands of standardized bronze components to a consistent specification across distributed workshops more than 2,000 years ago, verified not by legend, but by measuring the objects themselves. The next time a mass-produced object comes out of a box and fits perfectly with a part made in an entirely different factory, it is worth remembering that the same organizational problem, keeping thousands of separate hands producing to one shared standard, was being solved in Qin China for an army that was never meant to be seen by anyone at all.